We'll make a start now. So for this session, we have Daniel Murfet. Daniel is a mathematician at the University of Melbourne with interest in algebraic geometry, logic, and theory of deep learning. He was a signatory to an open letter to Ed Husic MP on to take AI safety seriously, and today we're hearing a talk on AI safety and developmental interpretability. So thank you, Daniel.
Yeah, thanks to the organisers for inviting me to give this talk. Hello, everybody. Nice to meet you all. It's been a pleasure over the last few days to meet a surprising number of people in the region interested in this topic. And I hope we'll continue to stay in touch and talk to us after this meeting. So I'm going to say a bit about my interest in AI safety and the particular brand of technical AI safety research that I'm doing with my friend Jesse here and a number of others called developmental interpretability. First, little movie. That's development. Okay, this is a picture of a neural network training. I'll say a little bit more about this particular project later on, just to briefly sort of give you a clue what you're looking at. Neural networks have to process a lot of information, especially large language models, much more information than they can represent individually in the nodes or neurons of their computational graph. So it's been observed empirically that neural networks do something which has been termed by some in the community superposition, which means that you think about the distinct kind of factors involved in the data. So if you're modeling animals, for example, you might have that animals are either nocturnal or diurnal. You might have that they're either land-based or ocean-based. You have a number of features that sort of have some axis of variation. And rather than storing one axis of variation per dimension, so you might know that GPT-3, for example, has 175 billion parameters. That's a point space dimension 175 billion. That might seem like more than enough to represent everything you want to know about animals, but the world is full of lots of other stuff that GPT-3 has to represent, and it also needs to compute on those representations. So it turns out that that's not enough to have like one dimension per factor in the world. So they represent more than one. That's what you're looking at. So this is a neural network representing or attempting to represent 6 factors of variation in 2 dimensions. It's only actually succeeding in representing 5 of them. It's the pentagon. At the beginning, it's only representing 4. That's not good enough, right? It wants to represent more. It wants to decrease the loss. The loss is this blue line, and you can see that, but it's a line decreasing stepwise here. As that line decreases, it's doing a better job of modeling the distribution, representing the factors of variation. And you can see that there's sort of distinct steps in its development, right, where it jumps from some particularly stable configuration to another one, which represents the data more accurately and is more complex. This green line here is a particular measure of complexity that comes from sort of mathematical theory of learning. I'll speak about it in a minute. But this is what we care about. Maybe not this particular model. This is a good toy model for getting started. But if we want to be able to have very advanced AI systems out there in the world doing lots of things, we'd like to understand what goes on inside them. And one approach to doing that is understanding how they develop. This is an example of such a development. Okay, so I'm going to come back to all that in a minute, introduce myself a little bit first. So I started life as an algebraic geometer. I did my PhD at ANU, Queensland, originally. I've done mathematical logic and more recently statistical learning theory. Been at UCLA and USC and Melbourne, so I'm a mathematician here since about 2015. I've become increasingly interested, first of all, just in understanding how deep learning worked. And the last year or so, increasingly I'm shifting most of my new research to AI safety, technical AI safety, or AI alignment, for the reasons many of you are here also. I'll say a bit more about my reasons in a minute. Yeah, most of this slide is like a bona fides thing, right? Like, I actually know how to train neural networks. I've been publishing this area for a few years. I'm not a machine learning person in the sense that I'm publishing 5 papers for Europe every year, but I am competent. I know what I'm talking about. And I'll flag this again at the end. Taking masters and PhD students in technical AI safety. So that's a direction you're interested in pursuing. Do get in touch. Okay, I want to show you 2 graphs, which are both quite concerning. This one, I think you've all seen in some form or another. This is the famous hockey stick graph. It shows the temperature variation last 1,000 years or so, and that big spike at the end, we know, is a problem. Climate change is a problem that is, of course, very well understood by the public as a result of lots of advocacy and science communication. Not only do people understand that the temperature is increasing, but they understand somehow that the implications of that increase are not continuous, not all of them, right? As the temperature increases, if you read the IPCC report, they'll be like, okay, at +1 degree, this will happen. +1.1, probably about the same, qualitatively speaking. +2, that's really different. This will happen. We have a sense that the gap between +0 over the sort of pre-industrial period and +1, that's 1 degree of additional warming, but it's not the same as going from +5 to +6. Right? Okay. So this sort of understanding of it's a complex nonlinear dynamical system, the environment, but the public sort of has an understanding at a qualitative level of various aspects of that change in a way that they do not understand this plot. So this is a graph taken from the GPT-3 paper, published in 2020, Language Models of Few-Shot Learners. It shows the scaling laws, sometimes called neural scaling laws. So the neural scaling laws were, I think, first published in 2017. It probably became sort of widely known in 2020. Actually, there was a paper before this in the same year by Kaplan et al., which is usually cited subject of scaling laws. So what are scaling laws? Well, the x-axis here is compute, training time. Not quite training time, because it depends also on the size of the model. So just the number of flops that are spent training the model. It's a function of the size and also how long you train it. Y-axis is test loss, validation loss. So how well it performs on some data that wasn't in its training set. So lower the better. Parameters over here. Okay, so if you have a model with 10 to the 5 parameters, the longer you train it, it's going to decrease and then kind of leave this frontier here. If you keep increasing the size of your model, you'll keep getting predictable increases in performance. And there's similar scaling, it's called a scaling law because of power law, because of the form of this relationship between the loss, measure of how good your model is, and the amount of compute you spend. So a log-log plot, that looks like a straight line. There are other scaling laws where you vary not the compute, but the size of the model and also the data set size, the amount of training. So when you hear people talk about training corpus for each iteration of GPT growing, they know how to scale that data set because of these laws. We don't understand where these laws come from, but these scaling laws are undeniably behind investment on the scale of billions of dollars going on over the last 4 years. We can see these and make predictions about where we'll be right now, and those predictions continue to hold. Nobody knows if, as we keep scaling up, this relationship will continue to be true, but people are betting a lot of money that it will be. Okay, so that's sort of like just the science of what's going on. This loss doesn't translate immediately into the felt sense of what it's like to interact with each iteration of these models, right? If you spend a lot of time, maybe with GPT-2, and then with GPT-3 in the playground, and then with GPT-3.5, and then with GPT-4, right? You can't go back, right? Play with GPT-4 for a minute, you go and talk to GPT-3.5, the free version of ChatGPT, and it's like talking to a drum. It's like, you don't know any calculus, so stupid. GPT-4 can get 70% on my undergraduate calculus. So I teach calculus here quite often. Some of you have taken classes. There was a calculus exam that I hadn't given yet. I gave it to GPT-4, it got 70%. Interrogating it, I think it understood it. It makes different mistakes to students, but it understood it. If it was like a kind of Turing test where I didn't know it was a student on the other end, I would think they were brilliant and kind of weird in some respects. Long division somehow had a lot of trouble with long division, but like the really complex integrals were completely fine. So that's a bit weird. But I wouldn't have questioned that it understood the exam. That's GPT-4. GPT-3.5 could not do that. GPT-2 would be ridiculous to even try. So what we perceive about these models is like those capabilities. Those capabilities are not on this plot. Nobody understands how to go from this plot, which we can predict, to the capabilities which we cannot. We're trying pretty hard, I think. But what we do know is that sort of unpredictably, as we proceed along these scaling curves, new capabilities emerge. And we don't know what's going to come out of the box next time we train one of these models. And that's like, in a nutshell, one of the reasons to be quite concerned about the prospects for humanity if we do not understand systems, we continue to draw from this urn. Yeah, maybe I wanted to compare this to the earlier picture a little bit. Yeah, so I mentioned that going from +0 to +1 degrees is quite different from going to +4 to +5. Right? The jumps in capability are also not necessarily of the same scale. This going from GPT-4 to GPT-5, maybe it's boring, maybe it's quite exciting. In the same way, +4 to +5 degrees might be quite exciting. Okay, so that's sort of the context. Paying attention to this as a scientist, you feel simultaneously thrilled by the fancy new toy and by the new phenomena that's being unveiled in front of you, something deep about learning and intelligence is being sort of unspooled 1 year at a time, paper at a time. At the same time, you can't help but feel a little bit of trepidation. But let me say a bit about like the scientific work we're doing to try and understand more of what's going on in this plot. So this is a very interesting graph from a paper from Anthropic, Context Learning and Induction Heads. Some of you may have seen. It's pointing to this particular region of the scaling curve. Not this exact curve that I showed you, but one from the earlier paper Kaplan. You can sort of see, like, as far as I know, the only way this has appeared is in like Chris Olar's talks. So I don't know if you really want to bet your life on this phenomenon being legitimate, but I think it's quite, at some level, pretty justified observation, which is that the scaling exponent, that power law, seems perhaps to change over the course of training, spending compute, from one particular slope to another slope as a result of some change in the network structure. So that represents the model reconfiguring itself to be better at learning, which is interesting. We don't, I think, have a conclusive understanding of what that change is, but the conjecture in this article, paper, you solidly argue, I would say, is that that change in the scaling exponent is due to the emergence of what they call induction heads, which is, as a logician, seems to me something like modus ponens. So induction heads say something like, if you see a pattern in your context, so context, just briefly, transformers are trained on a lot of data to predict next token. But in the forward pass, when they're sort of crunching the numbers on those tokens in order to make that prediction, there's a lot of intermediate activation. So the nodes in the computational graph take on certain values. We don't know exactly what's happening in that forward pass. But in-context learning refers to the capability of transformers within the forward pass to do something like learning. Not the outer loop learning, where you're changing the weights in order to minimize the loss, but online, without changing the weights, just the same way that you might do if I gave you a list of numbers and asked you to complete the even numbers. You would predict an even one. Probably the long-term weights in your mind aren't changing as I give you that token by token. And similarly, transformers can do this at certain scales. So maybe GPT-3 is the first time this appeared. And induction heads are sort of like some particular mechanistic detail of how that seems to be achieved. Okay, so that's an indication of this correspondence between the high level and the thermodynamic behavior of the system, scaling laws, and sort of microscopic structure. Induction heads. So that's a subject of mechanistic interpretability to understand what those are and how they emerge. That's the kind of science that we're looking to do more of and involve more mathematics in. I'm going to go rather quickly through this. I want to finish with plenty of time for questions. My personal reason for getting interested in deep learning is interested in mathematical logic and the emergence of logic and reasoning in machines. And more precisely, its emergence in machines suggesting that its emergence in us is part of a broader universal pattern of emergence of reasoning in sufficiently large-scale learning systems. This sort of original point of interest. It's a bit controversial whether or not current LLMs are like really reasoning. You'll find people arguing this point. I think it's a silly argument. They're reasoning. Maybe not in exactly the same way we are. They're not able to produce the same kind of long-term research agenda that humans would do, mathematics say. But whether or not they're doing reasoning in some reasonable sense is, I think, established beyond question by some of these examinations of what's going on, things like induction heads. Debate is over. The evidence suggests that maybe human-level intelligence is not difficult. Despite tens of thousands of people working in deep learning, most of them aren't really doing anything in terms of pushing the frontier. We could have gotten to the level of capabilities we have right now with a few hundred people. All the publications in Europe's ICML, ICLR, all the top conferences, they're making incremental progress that'll get and has gotten wiped out by like the next generation of large-scale models. So don't be fooled by the scale of activity. This is easier than it looks. And that's pretty astonishing. You're all sort of aware of the race dynamic that's going on. Despite the sort of aggressive progress and capabilities, we don't understand what's going on. We have some ability to predict based on the scaling laws, but we don't understand where the scaling laws come from. There's a couple of papers examining that, but there's nothing conclusive. So we're really pretty much in the dark. There isn't really much theory of deep learning. And nonetheless, progress continues, right? Okay, so AI safety encompasses a range of activities. I'm going to focus on AI alignment, which is sort of broadly speaking the problem of aiming a very intelligent system where you maybe get to configure the initial conditions, but if you do it wrong, not intervene later. So getting it right at the beginning becomes very important. This field has been called a number of different names, control problem, going back to the very founders of the field of artificial intelligence. This has been an active area of speculation, not research. These days it's called AI alignment. AI alignment contains many different parts. One of them is interpretability, which is itself kind of an old subject in AI. I don't want to diss anybody's work by saying it doesn't work. I think, broadly speaking, anybody working in interpretability, we can do something. And some of what we can do is very interesting and suggestive. But in very small systems, we can sort of have a detailed understanding of what's going on. Nobody, I believe, would claim that they have a good understanding of the non-trivial behavior like GPT-3. Depending what you count as trivial. We're very far from having kind of scientific understanding of what's going on in these systems that you would hope to have in the context of the previous slide where we're talking about, reasoning's here, these systems are passing calculus exams. You would hope to maybe be a bit further along on this front. Really not. Although it looks really fascinating, right? There's lots of interesting links between microscopic structure, macroscopic structure. Scaling laws are like these profound new things. People are turning up all sorts of interesting stuff in mechanistic interpretability. So there's plenty of stuff to do and interesting science to be done. But sort of like very far behind the 8 ball compared to capabilities. I'd also say that AI alignment is a very important field of technical study. That's why I'm working on it. And you have a background in mathematics, physics, computer science, and you're choosing what to do. Should do this. Because maybe your other career choices in this paper. Okay, why interpretability in particular? It's sort of people observe often and they come from a technical background like myself and read the alignment literature and you think about where you can contribute. It's a sort of technically oriented person. There's a number of places you can choose. And I know a number of people here are interested in agent foundations, for example, which is also very interesting. Interpretability sort of comes up a lot in alignment plans. Right? Someone lays out how they're going to make an advanced AI system safe. At some point, there's a bullet point that says, well, we detect deception. Or during training, before it stages a takeover, we turn it off. Because we know it's going to be planning. It's being a bit amusing about it. But if you cannot interact or understand the system except through behavioral evaluations, you're always going to be very susceptible to the system generalizing outside of your tests in a way that is just completely unanticipated. You're still vulnerable to that risk, even if you have some understanding of the system, because it won't be a total understanding. But in terms of reducing the risk of systems doing very strange things outside of training, having some understanding of what they're doing internally is sort of like a common sense thing to want to do. And that's what interpretability is about. Just to give an example that people often discuss, you'd be quite concerned. So suppose you could look inside the model and sort of basically figure out how complicated its thought patterns are. You ask it a question like, tomorrow when I deploy you, and I ask you to do this question on my calculus exam, what would you do? It goes away and does like 30 days worth of human planning. Well, students also study. Maybe that's a bit of in-context learning going on, but you prefer to like see some very straightforward sequence of operations that like vaguely has something to do with calculus, right? Rather than some sequence of operations that has to do with taking over factories in Nebraska. Okay, so that's an example of, well, if you could have some understanding of A, the algorithms being executed, and maybe the level of complexity, that would be some information, not a lot of information perhaps relative to the risks, but it's something. So complexity of algorithms that are being executed inside neural networks is one of the things you might want to study. So let me say a little bit about some technical work in that direction that we're doing. Okay, so this is like a little bit far from interpretability. I'll get closer to interpretability, of course, in the next 5 minutes. But this is some work that I've done with a student of mine in Lau and my colleague Susan Wayne, who's a statistician here at the University of Melbourne. Giving, I would say, the first theoretically well-motivated measure of complexity for neural networks in particular, but also a broader class of learning algorithms. You see over here is an estimate of the complexity of the learned algorithm in a network with about 2 million parameters, which maybe doesn't sound like a lot, but from a theoretical point of view, having a theoretically well-justified measure of complexity of the stuff, the algorithm that's been learned by the neural network is highly non-trivial. It's like a scalable way of doing that, or the learning coefficient. It's based on some mathematics on singular learning. What this shows here is a separation between like lower here is simpler. So this is over time. See that at the end of training, if you train it with a particular optimizer called entropy SGD, this algorithm that is learned is simpler than this one. We sort of know in advance that should be true, and this is a check. But the point I want to make with this slide is that some mathematics, singular learning theory, provides new ideas for a theory of deep learning, science of deep learning, which you can then develop, potentially deploy in the service of interpretability. Close to interpretability is some work we've just completed on the toy model of superposition. This was the movie I showed you earlier. So that's kind of sketched, maybe briefly, why that comes up in interpretability, but the interpretability group in Anthropic, Chris Olar in particular, would say that superposition is one of the key problems in interpretability. I'm not sure I completely agree with that, but it's nonetheless something widely studied by practitioners, not some made-up problem. So what you see when you open up this thread, which is very beautiful, I highly recommend it, is that they observe in training neural networks lots of interesting behavior, not only over the course of training, but with respect to some parameter they call sparsity. You see certain geometric figures appear in the configuration of the neural network weights. It's very fascinating. But complete mystery. Complete mystery we're able to, in some respects, resolve using theory that I mentioned. Just briefly explain what's going on here. So we're able to understand in some particular limit development of this toy model of superposition system over training. You can see the evolution of the network visualized here. It becomes more complex. It's going from a square to a pentagon. And that complexity is measured by some invariant that comes from the theory. Okay, so that gives you some idea of what we're trying to do with developmental interpretability, which is study systems, neural networks over the course of training. Take ideas from mathematics, statistical physics, and use those ideas to create tools to measure development. How can you see development? I mean, it's just the kind of accident that you can visualize the network weights in some way that's like human intuitive. Right? It's a tiny network. You can plot a picture of, oh, a square. Oh, a pentagon. Squares are simpler than pentagons. Something changed. That's like, not going to expect to do this in non-trivial systems, right? So if you can't look at pictures and you can't understand the weights, how are you supposed to know that anything changed? and in particular that something non-trivial evolved in the structure of the network. Well, you can always plot the loss. Loss here drops, and often people do look at drops in loss and say something happened there in neural network training. But in a large system like GPT-3, you don't see huge drops in the loss. It's a gigantic system. It's made up of the system learning many, many tasks, and they're sort of all added together. You're not going to see drops unless you graph on particular subtasks, in which case you might see some. But this measure here, which is this measure of complexity, is one of the ways in which you can sort of see inside and know that something has changed in the structure. Again, large system, this probably won't change in a way that reveals necessarily something internal changing. It's maybe it's swamped by many other effects. But it's like the first step in a series of theoretical developments which emphasize the role of phase transitions in the development of structuring. That's science. This is just some graphs showing you, I think given time, I'll explain this later. But I do want to mention that the approach we're taking to interpretability is partly modeled on the standard approach to understanding a different, highly important, nonlinear dynamical system, namely U. Rather, U 20 years ago, evolving from an M. So, embryonic development in living systems is not the same as neural network development. Many differences, but there are also many similarities, just based on the underlying mathematics and physics and constraints of the system. And decades ago, Waddington quite famously introduced this analogy for the development of embryonic systems, where they start at the top of some epigenetic landscape. It's now called. You read a paper on pluripotent stem cells, this kind of literature, you'll see discussion of epigenetic landscapes. This ball rolling down the hill and choosing which way to go at each point under some influence is a model for how skin cells develop from, say, stem cells. At each point, there's sort of a branch they can take. That branch is technically modeled by what's called a catastrophe or phase transition. And there's a lot of similarity between that mathematics and the mathematics, statistical learning theory that we're applying to try and study neural networks. Yeah, so we're looking at the toy model of superposition. Another paper out of Anthropic, as I mentioned earlier, is about in-context learning and induction heads. We also are applying our techniques to that. Pretty plot, next slide. Okay, so singular learning theory is a piece of math. It doesn't in and of itself say anything about AI safety or interpretability. So we're trying to do the work of bridging this rather abstract theory and the sort of ground truth of what's happening in neural networks, starting with very toy systems, because it goes without saying, science is quite 175 billion parameters is a lot. So understanding what's going on inside frontier models, no matter how you're doing it, it's going to be extremely difficult. It seems likely that you have to identify what I've termed here an axis of reducibility, right? Meaning some way of chopping up the problem in order to try and solve subproblems. You can do that by circuits, or by looking at various tasks within the data distribution. GPT-3 can do arithmetic. You can study its performance on arithmetic over time. Or you can look at training. Try to hope that over the course of development, you can see discrete moments where the structure changes in a qualitative way. So that's the approach we're taking. Such qualitative changes are called phase transitions technically. Phase transitions over neural network training has become rather a hot topic in the last year or two. There are many examples in small systems. So far, not really a theoretical understanding, apart from the work we're doing here. But at least in the toy model of superposition, we now have a pretty good match of theory and empirically observed phase transitions. The idea is that if you can identify these changes in structure as phase transitions and understand the change that each one of them represents, and put that together over the course of training, that might be a sort of independent way of approaching interpretability to, say, mechanistic interpretability, which is often done at the end and depends on choosing data inputs in a way that elicits the behavior of the study. So we need many different ways to try to probe the internal computational structure of these systems, and we're hopeful that developmental interpretability will add to that toolkit. And as I mentioned, there's sort of a standing behind this approach is a rather deep mathematical and statistical physical theory. Right. Yes, I think that's all I want to say about the technical material. So now I have an announcement. Okay, this is Jesse Hoogland. Many of you met him on Friday or over the last couple of days. So we've been plotting something for about 4 months now, which is a new AI safety organization, which we call Timaeus. So Timaeus is currently dedicated to this program of developmental interpretability research, which I've been telling you about. It's 4 of us: Jesse, Alexander Oldenziel, Stan Van Ingen, and myself. I'm here. Right now, Jesse is here. Usually he's not here. So it's a remote group. We're spread around Melbourne, the UK, and the Netherlands. We've been holding a few conferences around developmental interpretability in Berkeley, Amsterdam, just last week. There's another one coming up in November. Just been through a hiring process, so I think the application for that was spread through some of the mailing lists in the local community. So we've just done interviews for that, and they'll be starting next month. In future, we hope to be advertising more positions, sort of interpretability related areas. So keep an eye out for that and get in touch if you think that that's the kind of position that you might like to prepare for, help you to do the kind of work that will make you a good fit for those positions. And then become available. Another thing worth flagging is that we're trying to put together a course for second semester next year on mathematical methods of AI safety, to be held hopefully here at the University of Melbourne, so online. So I'd like to help out either preparing material or teaching material for that as a student. Please get in touch. And given some of the discussions on Friday, I want to make a plug for Australia as not the end of the world. Look at you, David. Given the topic for today, maybe end of the world is like ends of the earth. Like you might overestimate how much work in technical AI safety is actually going on planet Earth. But despite the problem seeming intractable and pressing, the number of people working on it, I've worked in tiny corners of algebraic geometry, right? With names that you would not comprehend. There are more people doing that than there are working on technical AI safety. It's absurd. Look, this chromatic homotopy theory is very cool. Probably not as important for the future of humanity as that situation has to change one way or another. I don't know exactly how it's going to change. But given that, it isn't out of the question for Melbourne, Australia, to play a big role in moving that field forward. All it takes is a number of people to be here, a number of students to decide to work on it, and this could become one of the centers to work on. There's some brands of technical ask. So I'd also like to end on an optimistic note. Maybe not because I am optimistic, but because it's good to end optimistic. Well, I do believe what's written. We've seen amazing fundamental progress in AI capabilities, right? Pure scaling may not save any safety, maybe a different kind of problem. But fundamental progress is possible. We're not restrained. It's not that we're fated to only make incremental progress from where we are now in the face of rapid capability advances. Breakthrough progress is possible. We should be trying to do it. Many people are trying. We in particular are trying. And please help. So I'll stop there. You can get in touch with us at these links. Thank you.
Fantastic. Thank you so much. Unfortunately, we've got another session in here right now. So if you have questions, please. I'll be able to hang